Okay, so we're going to start today with the second half of chapter 2, which is on a topic called resonance. And resonance is specifically in regards to the position of pi electrons. So pi electrons are electrons that are in pi bonds. Before we get too far along, firstly, can everybody hear me? And are there any questions about material from chapter 1 and the first part of chapter 2? Okay, perfect. Okay. All right, so are there any questions about the first part of chapters? So 1 was really a general chemistry introduction or review. And then 2, the first part of 2 is learning how to draw the line bond drawings of molecules. Okay, so just a few reminders. You should be going through the flashcards of your functional groups, because it's going to be important. I'm just going to write down here for just a minute that you can distinguish or be able to draw an ester, for example, versus a ketone. Okay, it doesn't matter what's over here. It'll just, a lot of times it's just going to say R, and that just means the rest of the molecule, most likely carbons. But what's important is being able to distinguish like this bit versus that bit. So those should be, you should be going through those a couple times a day just to make sure that you have them memorized. Okay, so if there aren't any other questions, we're going to get started. Hopefully we're going to finish this bit on resonance today and start on chapter 4. And hopefully get a good way into 4 tomorrow so that you're in good shape for your lab tomorrow afternoon. So like I said, resonance is going to be with respect to position of pi electrons. So again, I'll draw something here and then I'll erase it so I can make some lists. So if you have a compound that looks like this. Okay. This part in the middle, right here, that set of double lines represents a double bond. And remember, the double bond is a sigma bond and a pi bond. Oops, sorry about that. Okay, so there are 2 electrons in the sigma bond. And remember, that's made from head-on collision. And then there are 2 pi electrons in the pi bond component. And it doesn't matter. Most people just gravitate towards this line at the outside being the pi bond, but it doesn't matter which one you pick as being the pi bond. What matters is that you recognize that you have 2 electrons in the sigma bond. And for the most part, you're going to always just leave these. So sigma electrons, especially sigma electrons between carbons, are not reactive. So they're not going to be used for anything. Pi electrons are the useful electrons. So lone pairs and pi bonds are really going to be the most important part. So those are the pi electrons. And then the other thing when we talk about the resonance, so it's position of pi bonds as well as nearby lone pairs. So lone pairs you should be familiar with. Those are electrons that are on atoms that are not involved in a bond. Okay. So the difference between localized bonds and delocalized bonds is with respect to the number of atoms that participate. It's driving me crazy that it's crooked. There we go. Okay, so in a localized bond, for example, the pi bond in ethylene, this pi bond belongs only to 2 atoms. So there is no way or no likelihood that those 2 pi electrons are going to be anywhere other than locked in place between those 2 carbons. So that's what localized is meaning, locked in place. Okay. And if you have the slides in front of you, the image to help you remember locked in place is somebody in jail. So these pi electrons, they're useful. They can be used in a reaction, but they only belong to these 2 carbons. They don't belong to any of these hydrogen atoms. Okay. Now, when you have delocalized bonding, what you have is, and I'll give you an example of it in just a minute. Delocalized bonds is when you have pi electrons and or lone pairs of electrons that belong to more than 2 atoms. So these electrons are not locked in place. They are essentially, you think about it, like almost like smeared out or shared between a larger section or a larger portion of a molecule. So the reason that I have the image that I have on the slides, that's if you haven't seen Shawshank Redemption, you should. But in the movie, this is a spoiler, but I won't tell you the whole bit. There's a prisoner who's in jail and then he escapes. And there's a period of time where he's crawling through the jail, Shawshank, the prison. But you don't exactly know where he is. You just know he's somewhere within the walls and sewers of the prison. And so he's not locked in a jail cell anymore. He is spread throughout the entire prison. And until they find him, he could be anywhere. Okay, so delocalized bond just means that you have either pi electrons or lone pairs that belong to multiple atoms. Okay, so if you move on to the next slide, I'll show you an example of why it's very important to consider the possibility that a molecule may be participating in resonance. Okay. So you don't necessarily even have to write this next bit down. It's just, you could listen to what I have to say about it, and that may be enough just to sort of indicate the importance of this, of the topic. So when you use line bond drawings, which you're going to use extensively, they can trick you into only considering localized or locked in place bonding. The problem with that is what happens when you look at an actual reaction that takes place. Okay, now why this reaction takes place we'll get to in a later portion of the class. But what I want you to just write or pay attention to is this RxN. That just means I'm going to do a reaction. Okay. And in the course of this reaction, I'm going to make this species. Okay. Okay, so that species has 4 carbon atoms, and it has pi electrons here and a plus charge on this carbon. Okay. Now, if I take this species and I put it next to or in the same container as a chloride, okay, opposites attract. That's true in magnets, it's true in lots of different circumstances. But in this class, when you have a negative charge and you have a positive charge, the negative charge is going to come and be attracted at this carbon site. Okay, so we're going to perform the rest of the reaction, and then we're going to isolate our product, and you're going to see that you have a chlorine now stuck at that molecule or onto that molecule with a new bond at the carbon where the plus used to be. Okay. And so if I told you, well, we did a reaction and we got this product and this is what things looked like as we moved along, you shouldn't be surprised. Negatives are attracted to positives, and you make new bonds between the compounds. Okay. But what also happens when you figure out what your products are is you see this product. Okay, so this would be our unexpected product. Okay. So the problem with line bond drawings is this might look localized. But resonance is present, and we actually have delocalization. And what happens is these 3 carbon atoms, the 2 that are participating in the bond, and this one that's carrying the plus sign, those are 3 atoms sharing in the stabilization of the 2 pi electrons. Okay, so what resonance does is creates stability in your molecule. Molecule, or this would be an ion, cation. Molecules and ions that participate in resonance are going to be more stable than those that don't participate in resonance. So what we're going to do is we're going to break this up into a couple different ideas. The first is that we're going to talk about what we're going to call a resonance structure, and we're going to compare it to reality. Okay. The resonance structure is what you're going to draw. So you can have a series or a set of resonance structures. That you can draw on paper. Reality is going to be a mix of all possible structures you drew. So you're not actually going to be able to draw the real molecule. You're going to draw a set of structures that contribute to what is actually present. Okay. So that's the first thing that we're going to do. And then the second thing we're going to do is we're going to look for and learn patterns in molecules always participate in resonance. Now, this part of the learning, what we have to remember is we have to present material in a fluid manner, okay? Which means it's going to be easier to draw small molecules than large molecules. So in lecture, we're going to use small molecules. But the patterns will be the same whether the molecule is small or large. So when you're doing your practice, you're going to look for the patterns in large molecules. So that's where we're going. Okay, are there any questions before we start talking about what a resonance structure is versus what's actually happening in real life? Okay. So the example we're going to use is actually not an organic molecule per se, but we're going to use a polyatomic anion called carbonate. Okay. Now for some of this, you're just going to have to believe me, instead of going through drawing the entire, going through like the steps of drawing a Lewis structure. But when you draw a Lewis structure for carbonate, what happens is you end up with this. That structure uses, and we'll just put the 2 minus out here just to say that is this bit here, this is supposed to be a square bracket. I'm just being lazy and not drawing the whole thing. So I'm just drawing one portion of the bracket. Okay, so this is what you would generate if you use all 24 valence electrons that are contributing to the bonding of carbonate. Okay. But when you look at this structure, the carbon atom only sees 6 valence electrons. So it's not stable because it's not obeying the octet rule. So when you have cases like this, what you do is you use lone pairs of electrons from terminal or outside atoms to participate in multiple bonds, or like a double bond or a triple bond, to this carbon, so that the carbon will see an octet. So as it stands right now, this carbon atom sees 2, 4, 6 electrons. So it's missing one set of electrons. But which carbon atom does it come from, or which oxygen atom does the lone pair come from? The top, the right, or the left? Well, it turns out that there are 3 ways that you can draw this molecule. So you can take, let's say we're going to take this lone pair and make a pi bond. Okay, that's equally probable as saying that this oxygen made the pi bond. Which is equally probable as saying the right-hand side carbon, or excuse me, oxygen, donated the pi electrons here. Okay, now there's a couple things that I need to tell you that are based on experiment. Okay, the first is that all, and it's pretty much the most important, all the carbon to oxygen bonds in carbonate are identical. Okay. And that's based on looking at things like bond vibrations. Okay. So when you look at this molecule, this bond is equivalent to this bond, which is equivalent to this bond. Okay. This bond equivalent here, equivalent here. This bond is equivalent here, is equivalent here. Okay. The second thing that's really important to remember is that a bond is pretty much set. It's either a single bond or a double bond or some combination, a bond and a half maybe, a bond and a third. Okay, the pi bond doesn't move. Okay, so it's not jumping around this molecule. Each of these three is a resonance contributor. It's one way to draw the carbonate structure with the limitation that it appears as though this pi bond is fixed, but it's not. It simultaneously is on the right, on the left, and up here, all at the same time. So these pi electrons, 2 electrons in the pi bond, are spread out between 1, 2, 3, 4 atoms. Okay, so they're not locked in place between 2 atoms. They're spread out over 4 atoms. Okay, but these are the things you have to draw. Now, you can't really draw on a molecule these electron densities smeared. So you draw extremes. Okay. Are there any questions before we move on and start? We have to do a little bit of stuff with naming and learning positions before we start getting into how we're going to show these and the patterns of stability. Okay. So the first part of this is learning positional names. Right? So what we're going to have is this structure, okay, and we're going to compare it to this structure. Carbons that participate in a pi bond. Okay. Those carbons are called vinylic. Over here, you can see that I have a carbon bonded to a hydrogen, and I'm drawing this one so it's explicit. Over here, you have carbons bonded to carbons. So on the outside of this molecule, you have a lot of CH3 groups. Okay. So all of these carbon atoms, these carbons are one atom away from a pi bond. Okay. when they're one atom away, they're called allylic. Now, if instead of having just one carbon out here, you had a chain, you have vinylic, allylic, and then anything over here is called alkyl. Okay. So it's kind of like saying, this is my house, this is my next door neighbor, and then these are people down the street. Okay, so vinylic, allylic, alkyl. Those words should be on flashcards after today's lecture. Now, the reason I have this hydrogen here is because it is one atom removed from a pi bond. But this hydrogen is not called allylic. This hydrogen is bonded to a vinylic carbon. So this is called a vinylic hydrogen. So it's important for you to have these various names: vinylic, allylic, alkyl, and then determining, like when you're one atom away, whether you're considered allylic or you're considered vinylic. So it's only hydrogens that are really considered vinylic off of a vinyl carbon. If you have a carbon off a vinylic carbon, then it's allylic. Questions? Okay, so when we draw resonance structures, what we're going to do, this is section 2.8, which is called curved arrows. So curved arrows in resonance show how electrons would have to move in order to generate an equivalent or a representative resonance structure. The problem with curved arrows in resonance is the electrons don't actually move. You just have to show how they might move if it was allowed in order to go from structure A to structure B to structure C. So what you're going to have is you're going to have a structure. Oops. Okay. You're going to draw arrows on A such that you make structure B. Okay. If you draw on B, those arrows should indicate so that you can make structure C. Okay. So if you have a structure and you draw arrows on it, then you have to make a new structure. If you draw arrows on the new structure, you have to make another new structure. So curved arrows have to be drawn very carefully. Okay. So when you draw a curved arrow, it has to look like that. Okay? It can't look like this. Okay? You can't get sloppy and do that. Okay? You have to be clean. Now, hopefully, depending on when you're taking the second semester, hopefully sometime you will have a like handwritten work that has to be turned in. And when you do, you have to have clean arrows. This is called the tail. This is called the head. The tail is always going to start on electrons, never on an atom. Always start on electrons. They can be lone pairs, they can be pi bonds, but they cannot be atoms and they cannot be sigma bonds. So pi and lone pair. This part, the head, this can point at an atom. Okay. These things up here, where I'm putting this purple dot, it looks black, but it's purple. Those two dots on those black lines, those are called like barbs, like on a fishing hook. You draw one barb per electron. So if you want to move 2 electrons, you have to draw an arrow that looks like this. Okay. You can only move pi bonds or pi bond electrons, and you can only move lone pairs. Okay. But you can only generate 3 things. You're only allowed to do 3 motions. The first is that you can have pi electrons becoming pi electrons. So you just move the placement of the pi bond, remembering that it's actually just showing which atoms are contributing to the stability. You can take pi electrons and make them into a lone pair of electrons on an atom. So they go from a bond up to an atom. Or you can take lone pairs and make pi bonds. That's it. You cannot make a lone pair into a lone pair. That's forbidden. So these 3 motions are all you're allowed to do. Now the example on your slide has one of your patterns. And what this is you have 2 vinylic carbons, 2 carbons in the pi bond, next to an allylic carbocation. So that's what this is called, allylic carbocation. Okay. Now it's important to remember when you have an allylic carbocation, there are 2 hydrogens drawn, not drawn. Okay. So it had carbons with 3 bonds are cations. Okay. Now in order for me to show that these 2 pi electrons are spread out over these 3 carbons, I'm going to use a curved arrow to show the motion. So I'm taking them from being in a pi bond between carbons 1 and 2 2 being a pi bond between carbons 2 and 3. Double-ended arrows that look like this are considered resonance arrows, or you could draw 3 lines, which just means these are resonance structures. And then you move your pi electrons to the new position, and the carbocation charge would shift to the first carbon. So this carbon is this carbon. Okay, now you might be wondering, how do I know that I didn't just take this molecule with a spatula and flip it over? Okay, and the reason I know that is by bond vibrations. So bonds are springs. If my hands are a bond, are carbon atoms, and the space between is the bond. A single bond vibrates in and out slower than a pi bond, or a double bond, which is slower than a triple bond. Okay, so if these carbon-carbon bonds, this one here and this one here, if they're different, one's a sigma, one's a single, one's a double, then they're going to have 2 different vibrations. If they're the same kind of bond, then there's only going to be 1 vibration, because this bond will be equivalent to this bond. And when you do a bond vibration of an allylic carbocation, you see only 1 vibration. So all of the carbon-carbon bonds are identical in this compound. So this is one way to draw it. This is a second way to draw it, but the actual structure is a mix. It's a little bit like this and a little bit like this. We're going to look at some rules to help you keep track of what you're doing, and then we'll start looking at patterns. Okay. All right. So these are your golden rules. Rules for resonance. The first, avoid, and that's just a nice way of saying don't. Don't break sigma bonds. When you break a sigma bond, you're going to break a molecule into pieces. Okay, so breaking a sigma bond breaks your molecule into pieces. Okay. When you perform a resonance arrow analysis, if you have structure A that is 1 molecule, structure B has to be 1 molecule. You can't break apart into 2 pieces. Okay. The second rule is that you have to remember that second period atoms, like carbon, nitrogen, and oxygen, never exceed 8 electrons. So you cannot break the octet rule. Okay, so the easiest way to consider whether or not you have drawn a good structure is to see how many electrons you have touching any of your second period atoms. Okay. The third rule is that you can use more than 1 arrow. if necessary. So you can have multiple curved arrows on structure A to generate structure B. Okay. And the fourth rule is that you have to remember formal charge. The overall charge on the molecule must be the same on all resonance structures. So if a compound is neutral at the beginning, then you have to account for neutrality on the second structure, even if that means you have to use formal charge. And I'll show you an example of this in the next slide and then give you one to work on. Okay. Are there any questions about these rules before we start putting them into place and looking at patterns? Okay. All right. All right. So I'm going to do an example. And then I'm going to give you a molecule to work on. Okay. All right. And so the example molecule looks like this. Okay. Now, what is shown on the slide is I'm going to already have the arrows in place. So this is what you would see on the slide. Okay. And then it's asking, what does structure B look like? Now, one of the hints, and something that might help, is that all the sigma bonds in A are still in B, and they're exactly the same. Okay, the only thing, the only difference is placement of lone pairs and pi electrons. So remember, those are the only things you can move: sigma bond, pi electrons, and lone pairs. So if you take a look at this structure, you have 1, 2, 3, 4, 5 sigma bonds in this compound. Okay. So you can redraw that bit of it right off the bat, because this sigma bond network is identical to this sigma bond network. And rule 1 of resonance structures is you cannot break a sigma bond. Okay. When you look at the arrows here and you read what's happening, the way I would read this is say that a lone pair of electrons is coming down to be a bond between atoms. So this is lone pair becoming a pi bond. Okay. Here, I'm starting on the pi bond and I'm going onto an atom. So this is pi bond to lone pair. Okay. So when I come over to this structure, Now I just take these words and draw it. So over here, I took one lone pair and I made a pi bond. So I draw my pi bond. The oxygen had two lone pairs. Over here, it's only going to have one. Okay. Then I read what I did here. My pi bond became a lone pair. And they went onto that carbon atom right there with the dot. That's this carbon right here at this valley position. Okay. Now, if you look closer at structure B, you see unusual bonding patterns. Okay. Oxygen likes to make two bonds and carry two lone pairs. This oxygen is 3 bonds and 1 lone pair. So this oxygen needs a formal charge. Okay. Oxygen brought 6 electrons, that's from the periodic table. It gets 1, 2, 3 from the bonds, 4, 5 from the lone pair. The oxygen is a +1. Okay. Now this carbon atom is tricky because it doesn't have to be drawn, but there's a hydrogen there. Because there's 1, 2, 3 bonds shown, so this carbon has to have a hydrogen atom. Carbon brought 4. It gets 1, 2, 3 from the bonds, 4, 5. That carbon has a -1 charge. Now, if you add the charges, +1 plus -1, you get 0. And this original compound is neutral. Okay. Now, if there aren't any questions, I want to give you a structure to practice. I'm going to give you structure A. It's going to have arrows on it. And I want you to draw structure B and fill in the formal charges. Okay. So the structure I want you to work with has a 6-membered ring with alternating single and double bonds. Now this bit up here, this is called the nitro group. And nitro groups, they're called, it's a weird word. I'll have to write it out. It's called Zwitter ion. It's when you have a completely normal structure in which that's neutral, but you have atoms that always carry charge. Okay, so that's your structure. And the arrows are going to be here, here, and here. So this is structure A. I want you to take a few minutes and generate structure B. Does anybody need more time or want more time? Okay, so again, the first thing I would do is I would draw structure B with all the sigma bonds from A. So you would have a 6-membered ring, a bond to the nitrogen. Actually, let me, we're going to do formal charge afterwards. A sigma bond to the oxygen, and you would have a sigma bond to the oxygen. Now, the only reason I put the lone pairs here and not over here is because on A, I have an arrow that's involving that oxygen on the left. I didn't really do anything to the oxygen on the right, so I'm going to leave it as it is. Okay, so there are 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds in A. 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds in B. One molecule, one piece here. Okay. Now I go back to A and I look at my arrows and I figure out what has been shifted and what has been left alone. This bond here, this pi bond, this, like, I view this 6-membered ring as a clock. So this is like the 10 o'clock. So 10 o'clock to 8 o'clock, that pi bond is identical. So it goes right back where it was. Okay. This pi bond from 4 to 6 o'clock, this one is showing being moved in position to being a pi bond between 2 and 4 here. Okay. Now, if I don't have this resonance arrow, I would violate the octet over here. So this pi bond is showing going from midnight to 2 to being between midnight and nitrogen. So I have a pi bond here. Okay. This pi bond is going from being between nitrogen and oxygen, and it's shown coming up to become a lone pair. So I'd end up with 3 lone pairs on that nitrogen. Okay. So the sum of the formal charges here, we have a +1 on the nitrogen, a -1 on the oxygen, so that compound is neutral. So we have to have formal charges on this molecule so that it is also neutral. Okay. Now, if you look over here, this oxygen atom is exactly the same here, so it would also have a -1. This nitrogen is making 4 bonds and has a plus charge. This nitrogen is making 4 bonds, so it'll have a plus charge. Okay. This oxygen looks just like this oxygen, so it's going to have a minus charge. Okay, now it looks sort of like we're done, but the overall sum, -1 plus +1 -1, is not 0. Okay. So what you have to remember are all your tiny little hidden hydrogens. There's a hydrogen here to complete the octet, which means there's a hydrogen here. So this carbon is only making 3 bonds. So carbon brings 4, it's participating in 3 bonds. There's your +1 charge. Okay, so now you have -1 plus +1 plus -1 plus +1, and that's 0.
Whenever we're indicating like a positive charge and we don't have the hydrogen, or do we have to draw the hydrogen out?
No, you don't have to. So that's fine. Because even if you don't draw the hydrogen on the carbon, it's still there. What you can't do is like over here, be like, I have to remember there's a hydrogen there and just draw a line. Because if you just draw a line and don't put a hydrogen on there, you've just drawn a CH3 group. So if you're going to show hydrogens on carbons, you have to write the H. Does that make sense and answer your question?
Yes, thank you.
Okay. All right. Any other questions before we look at patterns? Okay. All right, so there are 5 patterns to recognize. The first is called the allylic lone pair, which means you have a lone pair of electrons, one atom away from a pi bond. Okay, because allylic means next to a pi bond or next to vinyl carbons. So there's a few examples. This would be like the classic allylic lone pair, okay, which you could bring these electrons down, these electrons up. So we have lone pair becoming pi bond, pi electrons becoming a lone pair. And we would make this. Now, technically, allylic means a carbon atom adjacent to a pi bond, but you can have variations on that because there are atoms that, other than in this case would be carbon, that like to carry lone pairs, like nitrogens and oxygens. Okay. So you could have this species, oops, and have a lone pair, one atom away from a pi bond. Oops, this isn't supposed to be an oxygen. Sorry, I'm getting ahead of myself. Lone pair, one atom away from a pi bond. Bring them down, kick them up. Okay. The next one that follow is similar. Is this lone pair adjacent to a pi bond. Bring them down, bring them up. The up and the down is just the way I interpret it. If you don't have to do it like that or say it like that. Here's another example. Bring these down and up. You can even get real crazy and have like a nitrogen. That. Down and up. But if you look at these 4 options, they're similar to this, where you have a lone pair on some atom adjacent to a pi bond. Lone pair adjacent to a pi bond. Lone pair adjacent to a pi bond. Here and here. Are there questions about the allylic lone pair?
So these patterns are just indications that they would have other forms of this?
Yep, that they would have resonance.
Thank you.
Yep, so the thing to remember, like, is that if I take these off, this is small, but let's say you had a compound that looked like this. Okay, that's a lot of stuff going on. But if you look carefully, this part here is the same as this part here. So this molecule would have a resonance structure. That looks like this. So it doesn't matter how fancy the molecule is. As long as you see a pattern, you will have resonance.
Thank you. That answers my question.
Great. Okay, the second one we've already looked at. The second is the allylic carbocation. So in that case, you have to have a plus charge on an allylic carbon. Okay. You move electrons, not pluses. The pluses end up getting moved or shifted in position because you've shown the electron motion with the curved arrow. This motion, this results from these electrons being moved. Okay. The other part of a allylic carbocation is that you can have molecules that have what's called conjugation. And conjugation is when you have alternating single bonds, double, single, double, single, double in a long chain. So not only is this, it's allylic here to this pi bond, but all of these other pi bonds can also participate. So I can move like this and generate that, and then I didn't draw my molecule very big enough. This can come down. Like that, and you can keep that carbocation allylic to all the different pi bonds in your structure. And you can just have a long chain of conjugation and stability of the carbocation. Good on that one? Okay. The third and the fourth are essentially mirrors of one another. The third is when you have a lone pair adjacent to a pi bond, or sorry, yeah, no, adjacent to a positive charge. So one of these carbons would come, or lone pairs would come down, and you would generate this neutral species here. Okay. The fourth is the opposite motion of this, but it has a different name. Its pattern is pi bond between two atoms with different electronegativity. So if you consider this molecule of acetone, this carbon is less electronegative than oxygen. So these pi electrons are, this bond is already polar in that direction. So one of the resonance structures would be those pi electrons up on the oxygen atom. So these are literally just reversing the order of what you're doing. Okay, so one thing I want you to kind of tuck into the back of your mind is that these two are resonance structures and they represent extremes of the actual structure. What I'm not saying is that this structure is as good as this structure. So it's not like saying 50% of the contributor will look like this and 50% would look like that. That's not true. But they're both contributing to the structure. Questions about those two? Those two are usually pretty straightforward. And the fifth one is the best because it's super easy. All right. The fifth pattern is conjugated bonds in a ring. And the most common is the six-membered ring that has alternating single and double bonds. Okay. Now you can move clockwise or counterclockwise, it's your choice, but you have to be consistent. You can't start in one direction and end in the other. Okay, so you either, I have mine going, I feel like they're going in this direction. You could have drawn them towards the right, but you can't do like this one coming up and then this one coming up like this. That's bad because you're going to end up way over violating the octet on those carbon atoms. All right, the last part of this chapter is to look at how molecular orbital theory will help us in stabilizing our resonance structures and our pi bonds and lone pairs of electrons. Are there any questions about the patterns before we look at molecular orbital theory diagrams? Okay. Okay, so now we're going to use molecular orbital theory to stabilize resonance. So what we're going to do, we're going to start with the allylic carbocation, which looks like this. Now, if you ask, does valence bond theory tell you anything about this? Valence bond theory, kinda. It'll explain like the bond angle and the hybridization, but it doesn't really help you with understanding why 3 carbon atoms are participating in stabilizing this structure. Okay, so we're going to do this. There's only 4 steps in doing this. Okay, and I want you to do the same 4 steps every time, no matter what structure you're asked to analyze the MO theory. Okay, because this is all you have to be able to do. The first thing you have to do is draw the resonance structure. It's essentially resonance structure B. So this is A. You're going to draw arrows on A to make B. So those pi electrons become pi electrons in a different position in the molecule. And we have that other resonance structure. Okay. The second thing is you're going to find the number of atoms used in the resonance. Okay, that's not spelled right. So how many atoms did you need to include when you stabilized this allylic carbocation? Okay, you used the two electrons, or sorry, the two carbons that were in the pi bond, as well as the carbon that carried the positive charge. So you used 3 carbon atoms. Okay. 3 carbons means you need 3 different p orbitals to make 3 molecular orbitals. Okay. So you go to your energy level diagram, you draw 3 lines, low, middle, high. Wave 1, wave 2, wave 3. And now the last thing is how many electrons were stabilized by the resonance. That you get from your drawing. You go back up here, and all you moved or allowed to participate in resonance were 2 electrons from this pi bond. Okay. So you put them in the lowest energy molecular orbital. Now, if you like the drawings of how the p orbitals line up, this one would have all of the positive lobes pointing up, 1 from each carbon, all the negative lobes pointing down. And you would see, when you do that, that you get no nodes. So you have no breaks. And all 3 of those carbon atoms are helping to stabilize those 2 electrons in the pi bond. So those 2 electrons are smeared out across those 3 atoms. Okay. This molecular orbital has 0 nodes. This would have 1 node. This one would have 2 nodes. Even though these are unoccupied, they have to be included. Would you like time to do, let's do it as like on your participants poll. Do you want to do one on your own? Or do you want to move on? The next couple slides, we just really have to jump to the very last one and then move on. Okay, so I have 6 votes for doing one of your own. Okay, 9 votes, perfect. Okay, that's the majority, I think, today. Okay, so what I'm gonna do is I'm gonna leave some of this up here. Okay. And we're just going to do a new molecule. Okay. All right. So the molecule I want you to think about is this one. Okay. Now, when you get to number 2 and you count the atoms used in the resonance, the number of atoms involved in resonance does not have to equal the number of atoms in the compound. You only count the atoms that are helping you to stabilize electrons. I will be right back. I'm going to give you a few minutes. Okay, does anybody need more time? Okay. So the first thing that you do is you look at your structure that's given, find the pattern of resonance in this molecule, and draw the second structure. Okay. So in this case, you have a pi bond, so you have vinylic carbons, and then you have an allylic lone pair. So that's what this pattern is, the allylic lone pair. This carbon atom up here is not involved in the allylic lone pair. This is just a regular alkyl carbon. Okay. So when you draw the resonance, you bring your pi or your lone pair down into a pi bond, your pi bond up into a lone pair. Okay. You redraw. Now the pi bond is here, and the allylic lone pair is out there. Okay. So only, you go to rule 2, the number of atoms used in resonance. This carbon participated, this carbon participated, and this carbon participated. This one out here did not. Okay. So 3 atoms were used in resonance. Okay. You don't really need this. It could be carbon or it could have been an oxygen. It doesn't matter, but the number of atoms, 3 atoms, you use 3 p orbitals, you make 3 molecular orbitals. Okay. And then you look at how many electrons were stabilized. You could just count count your resonance arrows and multiply by 2. So this arrow moved 2 electrons. This arrow was 2 electrons. That's a total of 4. So you come over to your molecular orbital diagram. 1, 2, 3, 4. Are there any questions about how to do that? I would practice it a few times before we go. We're going to skip all the way to the last slide, which is 2.11, assessing relative importance. Okay. All right, so if you have the slides in front of you, what you have is a picture of some Harry Potter people, the Malfoys and the Weasleys, I guess is their name is. Okay, just like Malfoy says, not all wizarding families are equal, not all resonance structures are equal. Okay, so if we look at this structure, this is called acetate. Okay, this is one resonance structure. I'm not going to draw the arrows, I'm just going to draw the structures themselves. The arrows are on the slides if you want them. Would be a good practice for you to draw the arrows and say this is A, B, and C. And you see if you can draw the arrows to go from A to B and then arrows on B to go to C. Okay, so if you have the slides in front of you, what it says underneath it is okay, not significant, okay. And what that is telling you is that this structure A and structure C contribute more to the overall stability than structure B does. Okay. So you should be able to look at a set of resonance structures and, excuse me, identify relative significance. Okay. And there's 3 rules that you use to gauge significance. The first is that you want, or the better structures will have all atoms with an octet. Okay. So even though these oxygens are carrying negative charges, they still see an octet. But this carbon in the middle doesn't see an octet. So this lack of octet here for the carbon is why structure B is less significant than A and C. In A and C, the carbon atom here in the middle has 8 electrons. The second thing you want to do when you're trying to determine relative significance is you want the fewest atoms possible that have to carry formal charge. Okay. And the third thing to consider is if you have multiple charges, they should be as close together as possible. So they should be on neighboring atoms and not spread out over the entire structure. So when you practice these, if you draw a resonance structure that you don't see in the back of the book or in the answer guide, it's probably because it's a not significant structure. So if you would do that and you would want me to check it and see if it's a valid resonance structure, I'm happy to do that. So if there aren't any questions about the resonance portion of this, we're going to move on into chapter 4. Oops, that's not what I wanted to do. Okay, so we'll move into chapter 4. Let's see, where is it? Here we go. Okay. And we are going to start looking at the simplest family of organic molecules, which are called the alkanes. All right. So chapter 4 is called alkanes and cycloalkanes. Now, we're going to very likely tomorrow need model kits. So if you have one, make sure you may want to have it handy when you are in class tomorrow or watching this video. Okay, so an alkane is the simplest family. Okay, alkane is a functional group. It just doesn't really have, it has no heteroatoms. It only has carbons and hydrogens. Okay. You have only carbon to carbon single bonds and carbon to hydrogen single bonds. Okay. And what that means is that these are nonpolar molecules. They're all nonpolar covalent bonds, and the molecules are nonpolar. They're not particularly useful unless you need a fuel, because they burn very, very well. And they generate a lot of heat when they do so. And the heavier ones are good solvents because they don't really interact with anything, and they're completely, for the most part, irrelevant biologically. Okay, so cycloalkanes, this word cyclo means they're rings. So alkanes are chains, straight chains or branched chains. So straight chain or branched alkanes. Branch just means they have pieces coming off of there. They all have the formula CN, so N would be some number greater than 1 or bigger, and then H 2 times that number plus 2. Okay, so if you have a 5-carbon alkane, you would say 5 times 2 plus, oops, wrote the answer. Oh. 5 times 2 plus 2 is 12, so you would have C5H12. Okay, so you don't have to count necessarily all the little hidden hydrogens. Okay. When you have an alkane, it's called saturated. And it means all your carbon atoms are bonded to the maximum number of hydrogens. Okay, so saturated is full. So the carbon atoms are full of hydrogens. Okay. The last letters, when you name your alkanes, they're all going to have an ending of ANE. Okay, so for example, methane, ethane, propane, hexane, decane, they all are, that ane ending tells you that it's an alkane. So we're going to learn how to name alkanes. This is kind of a long process, but it's really one of those things that you're going to have to practice. But I'll give you the rules, and then we'll do a couple examples, and then you will, the homework will help you practice. Okay, so we're going to break this up into pieces, and what you end up with is called a locant. Then you have called a substituent. And then you have a parent. Okay. A locant is a number. A substituent is something that is bonded to the parent, and the parent is the longest chain, continuous chain in the molecule. Okay, so this is what you start with, is your parent. So rule 1 is you're going to find the parent. And that's going to be a chain. And it's going to be the longest continual carbon chain. Okay. Okay. So then what you're going to do, once you have your longest chain, is you're going to number your parent and we're going to say this in both directions, and I'll give you an example of what I mean. Okay. So what that means is you're going to start at one end and number to the other. Then you're going to reverse direction. So for example, you could write 1, 2, 3, 4, and then reversing directions would be 1, 2, 3, 4. Okay. And then once you have that number, you're going to pick the best set. Okay. And what that means is you want the first substituent, so something coming off the parent chain, needs to have the lowest number possible. And the number is the locant. So it's telling you the position of a group off a parent. Your third rule is to identify the substituents. And substituents are going to come in 2 types. They can be alkyl groups, which are carbon-based groups, carbon chains, or they can be halogens. Now, there are more complicated examples, but this is where we're starting. You got to walk before you run. So your substituents will either be little carbon groups, or they're going to be halogens. Okay. And the fourth rule is that you write the name as a continuous sequence. If you have multiple locants, locant numbers are separated from other locants with a comma. Locants are separated from words with a dash. So like 2, 2, 2 dash chloro. Okay, so you need commas in a different position than you need a dash. Does everybody have these words down, the rules down, so that we can start identifying a parent chain? Does anybody need more time? Okay, I'm going to erase this. All right. All right, so if on the next slide, if you have them, you see a molecule. It's pretty complex, so I'm just going to draw it one time. And so when you start, okay, you have to number your chain in order to find the longest continuous series. Okay. All of these sigma bonds can rotate, so don't be afraid to turn corners. Okay. So I'm gonna do my numbering in green, and then I can erase the numbers to see if we can find a better chain. And I'm gonna have to, if you guys don't mind, if you have 5 extra minutes, I'd appreciate it if you could stick around, because this will be, we'll get to a good place if we can get through this slide. Okay, so if we say, I'm just gonna draw dots. 1, 2, 3, 4, 5, 6, 7. Okay, so that's one possibility. 7 carbons in the chain. All right, let's see if we can do any better. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's better than 7, so that's good. That's a possibility. Let's see if we can get anything longer. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So we've looked at a couple different pathways, and we found a 7, an 8, and a 9. Okay. 9 is going to be your parent. There's no longer continual chain within that compound. Okay. Now the second rule is that we have to number it. I'm going to leave those dots, but I'm going to number in, I'm going to try one of my skinny markers and see if you guys can see them, because it's going to get tight. Okay. Ooh, that's nice. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so that's one direction. Then I start here and I number backwards. 1, 2, 3, 4, 5, 6, 7, 8, 9. Any carbon piece, like this one out here, this one out here, this one, and this one that aren't named, or aren't numbered, those are substituents. They're pieces off of the main chain. I like these skinnier markers better. Okay. So now we have two pathways of numbers. We have a red pathway and a blue pathway. And if we start with the blue pathway, we have to write down the numbers where we have the carbon numbers where we have a substituent. So we have a substituent at carbon 3, a substituent at carbon 4, a substituent at carbon 5, and a substituent at carbon 6. If we use the red numbering, our first substituent is at 4, 5, 6, and 7. And then you compare the numbers. Okay. Since 3 is less than 4, this is the correct number pattern. Okay, so the blue numbers are going to be used to name this compound. Okay. All right, are there any questions about that for today? And then I'm going to write up some things that I want you to memorize and put on flashcards. Okay, we'll use a simpler molecule when we start getting going with naming. Okay, so what I want you to memorize are the numerical prefixes. Okay, so I want you to write a list, number of carbons, and then the prefix. Okay, and you have to memorize the list up to 10. Okay. If you have a 1 carbon alkane, the prefix is meth. So the compound would be methane. So ane means alkane, meth means 1 carbon. 2 carbons is eth. 3 carbons is prop. 4 carbons, bute. Okay. These are historically relevant names. Once you get to 5 and below, they make sense, they're numbers. Okay, so this is pent. So pentane, 6 is hex. 7 is hept, H-E-P-T. 8 is oct. 9 is non. 10 is dec. Okay. So a 10 carbon alkane would be called decane. 9 carbons, nonane. 8 carbons, octane. Heptane, hexane. These, like I said, these are the hardest, but only because they don't represent a number. Okay. All right, I appreciate very much you sticking by a couple extra minutes. Are there any questions before we end for today? I'm going to switch to these skinnier markers because they work so much better. I get more room. Looks nicer too. Okay, so I will post this recording as soon as I get it from Zoom, and I will see you tomorrow. We're going to, I wouldn't say we're going to pick up the pace, but we ideally will get all the way through this chapter tomorrow. So you're on time for lab. I mean, you're, excuse me, ready for the lab. I see there's some chats, but okay. Okay, all right, great. Have a good rest of your day, everybody. It's kind of cloudy, but rain's coming tomorrow. I will talk to you guys tomorrow. Oh, go ahead.
Thank you, I appreciate it.
No problem, Hannah. I'll talk to you guys tomorrow. Bye.